So today we're going to be looking at friction, and more importantly, we're looking at limiting friction. So this is when the friction has been maximized, but the particle isn't actually moving. It's just on the point of moving. So limiting equilibrium. Having a look at this diagram here, when we first started to look at calculating friction with the coefficient of friction, the first thing we had to consider is whether or not there was enough force to make the object move. But that was on a horizontal surface. Now we're on an inclined plane. To consider whether or not a particle is moving, we need to look at the natural driving force. The natural driving force comes from the parallel component of the weight. That will always be acting down the slope and wanting to make the particle move down the slope. Only friction and external forces will stop this from happening. So on a smooth slope, it's definitely going to go down the slope. On a rough slope, depending on the coefficient of friction and the value of R and the angle itself, we will then be able to deduce whether or not it's moving. So in this first example, let's try and consider whether or not the particle's moving. Well, the coefficient of friction is 0.2. So we have a 5 kilogram particle, which means it has a weight of 5g. Here we have components. Since we have a 30-degree incline, our components for the weight, our parallel perpendicular components for the weight, are 5g cosine 30 and 5g sine 30. We have our reaction force as usual, and since we've been told this is a rough slope, here is the friction. Okay, so that's the diagram complete. Let's actually try and work out what's happening with these forces. We're told the coefficient of friction is 0.2, so I'll write mu equals 0.2. We'll use that later. Let's start by resolving perpendicular to the plane, perpendicular to the direction of motion. R equals 5g cosine 30. Now let's resolve parallel to the plane. If the particle is going to move, we don't know if it is, but if it is, it will be moving down the slope. So I'm going to choose down as the positive direction. If the parallel component of the weight is more than the maximum friction, then this particle is going to be on the move. If it's equal to or less than the maximum friction, then we have a stationary object. Okay, so let's resolve. I'm going to do the forces in the positive direction minus the forces in the negative direction. If I get a positive answer, it's moving down the slope. If I get a negative answer, it's not moving at all. So let's compare. 5g sine 30 minus mu r, so that's 0.2 times 5g cosine 30. That equals 16.0 to 3 significant figures. So actually, the parallel component of the weight is enough to make this particle move, and it's moving down the slope. Well, now we're going to add an extra force. We're going to add in the force P. And we want P to keep this particle in limiting equilibrium. So let's just add in that force and some components. We'll have P sine 30 and P cosine 30. So if P is holding this particle in limiting equilibrium, the forces in the direction of motion should balance out. They should equal each other. So let's go again. This force P is going to change the value of R, so I'm going to recalculate that. So resolving perpendicular, R equals P sine 30 plus 5g cosine 30. I'm just going to rearrange that into the form of a simultaneous equation. R minus P sine 30 equals 5g cosine 30. So now resolving in the direction of motion, resolving parallel to the inclined plane. Let's take all the forces up the slope should equal all the forces down the slope. So P cosine 30 plus the maximum friction, so 0.2 R, should equal 5g sine 30. So I now have two equations in the form of a simultaneous equation. I'm ready to solve these. I'm just going to put these into the equation solver on my calculator with the correct coefficients and get the answers there. So into the calculator, and we get two answers. R equals 50.7 newtons and P equals 16.6 newtons. So to keep this particle in equilibrium, we need a horizontal force of 16.6 newtons. That's to counteract the forces that would make this slide down the slope. Here's the important part. This is not the only form of limiting equilibrium. All we've done here is stop the particle sliding down the slope. Any less force and it would slide down. We could have limiting equilibrium in the other direction, where we've increased P enough that we're about to be moving up the slope. So both of those cases, the particle is stationary. It's either on the point of slipping down the slope, or it's on the point of sliding up the slope. So two potential movements. The difference between them, when it's on the point of sliding down the slope, the friction is counteracting that, and the friction's going in the opposite direction, up the slope. When the particle's on the point of sliding up the slope, once again, friction is counteracting that movement, and friction needs to be modeled going down the slope. So both of these cases need to be considered as limiting equilibrium. So let's switch it around. Let's add the friction, but down the slope this time. So resolving perpendicular, this time around we get r minus p sine 30 equals 5g cosine 30. And resolving in the direction of motion, we get p cosine 30 minus the friction, rather than adding the friction, equals 5g sine 30. I could have written this as p cosine 30 equals 0.2r plus 5g sine 30, but I'm anticipating the simultaneous equation, so I'll just put it all on the left-hand side. Okay, back to the calculator, into the equation solver, and what do we get? We get r equals 64.0 and p equals 43.1. So these are the two possible answers for the amount of force needed to hold this particle in limiting equilibrium. Needed for this particle to be just on the brink, just on the point of about to move. One of them, it was about to move and slide down the slope. The other one, it was about to move and slide up the slope. The direction in which we modeled friction was the determining factor. Okay, so look out for that. Some questions will ask you for the minimum force needed. Some will ask you for the maximum force needed for limiting equilibrium.